Alright, so thanks everyone for joining. I have been provided a list of questions already, with some questions from the students, few from Akash, then Shiva Guru, and some more. So let's go over them one by one. One of the question asks me the meaning of element deletion versus elements being cracked. Now, for these two applications, of course, you must have seen this in an assignment where we were trying to use various material laws where a spherical impactor was impacting a plate, and then when plate is breaking, you are deciding whether element is supposed to be deleted or whether it is supposed to be cracked. So the element deletion, when we do that, or why do we do that? Whenever your elements are getting deformed or stretched beyond certain level, let's say beyond reality, after which they are supposed to be elongated to an extent where they are not going to maintain their shape anymore. Those are the times when they would start getting into the non-physical deformation modes, more like hourglass modes. We don't want that to happen. So what we do instead is we simply take them out of the simulation. That means we delete them. Now, element deletion causes some side effects. You are going to lose the mass that element represented. You are also going to lose the energy from your system, which that element was carrying so far. So if that element was carrying some internal energy so far because of this deformation, it's going to be deleted from the system. So you'll see some error because of that. So as long as your element deletion is in control, with respect to rest of your simulation, you will not see much of a problem, but eventually it comes under your energy error as well as mass error eventually. Now, elements being cracked. The application of elements being cracked is mainly in the studies where you're trying to study the crack propagation. You hit a bullet on a glass, or you hit a stone on a glass door, and you are trying to see how the glass door or that glass is going to shatter, and whether those shattering pieces are going to be damaging to the thing sitting inside that glass door or something else. There are many such studies that happen for such reasons. If I'm trying to also simulate how my windshield is going to break for a car, sure, those are the places where you'll try to see how the element is being cracked. So element being cracked has a definite advantage over element deletion, that here you are not deleting the element, but you are only splitting the element into two parts based on at what point you had a maximum force and at what point you have a very minimal force, and probably your shock wave is going to pass from this point to that point, and that way the element gets cracked. Now, element cracking has other expectations as well. In some of the newer algorithms I have seen around, while cracking the elements, they also try to remesh the part that is still there. That means if I'm hitting a stone on a windshield of a car, in the reality, you will see that wherever the stone hits, you'll see a huge dent there, which has turned mostly white. That means very small particles of glasses have formed there, or they have separated from the mainland glass. And from that particular point, you'll see radially all the cracks are going outward, and so on and so forth. Now, unless your mesh matches exactly this pattern of the cracking of the glass, you are not going to see the exact crack pattern in your simulation. So you need your simulation to adapt to which way these cracks are supposed to propagate. And that's where these element remeshing techniques are used. Of course, when you are trying to crack the elements, the newer methods are cheaper, but eventually it's sort of a detail that doesn't hold a lot of purpose if you're trying to do a crash analysis. So it really depends on what is the objective of your study. If you're trying to do the crash analysis with the usual objectives, where you're trying to measure the deformations, how you're trying to see how your vehicle components are getting crushed or whether they are getting bent or they're getting buckled, or how your occupant is going to move against the airbag. All these things don't really need element deletion or element cracking as well. Element deletion is needed when you're trying to decide whether some particular component is going to break ever. For example, if you do some offset crash, let's say 10, 15 degree or no, 5 degree offset or 40 degree offset. Well, there are such tests. You can find out about that. SORB. Okay, but it means a rigid barrier offset test. It's one of the popular ones where the pole or the barrier stands right in front of your car tire. Let's say right tire or left tire. And when the car hits there, only the components that are connecting the tire to the rest of the chassis and rest of the frame system, they are getting crushed because those are the ones which are under the maximum stress. If they don't get crushed, then your car is going to turn around into the barrier and it's going to face even more damage. So what companies would try to do is they would try to break away the tire by maybe the cutting off the lower suspension arm and things like those. Now, when they want to cut these off, in reality, they really break off by either elongation or by shear. In FEA, element deletion is used, and this is where element deletion is useful because now we are trying to represent the reality as well. So both of them have different purposes. Now moving on, implicit versus explicit. So there was a special slide for this when we spoke about this topic in the lectures as well. Implicit time integration is used where your time step needs to account for larger deformations, but overall the entire deformation of the system or the simulation is small. So small deformation problems will go with implicit, large deformation problems will go with explicit. The cause of deformation in implicit is pure force. It's dynamic. For example, the vibration created by the system when you're pressing it on one particular point at a particular frequency. These are dynamic forces that are getting generated in your system. Now, these forces are definitely going to cause some damage, but this is all implicit. If you're implying pure force, that is again an implicit analysis. Whereas in explicit method, all the deformations you'll see are caused by velocities, accelerations. So if you are doing a sled test or if you are seeing an occupant hitting against an airbag, here the velocity and acceleration with mass and inertia is getting involved because the occupant is moving it at such a high speed and occupant itself has its own mass. Because of this, whatever force is getting generated at that very particular moment, that is causing all the damage. But this force keeps changing. When the occupant hits the airbag, he's going to be decelerated pretty badly if the airbag doesn't do its job properly. That means this deceleration itself is going to represent all the jerks that you are going to experience as an occupant. So velocity or acceleration with mass or inertia, these are the ones which are causing you the damage here. So momentum and angular momentum, to be precise. Now, mathematically, you might have seen in one of the slides, you're trying to invert the matrices. In case of implicit, you're trying to inverse the K matrix, which is stiffness matrix. Stiffness matrix is one of the most complicated matrices in the whole FEA system, whereas mass matrix is the simplest one, where you have the numbers only on the diagonals and nowhere else. So explicit matrix or explicit method involves the inverse of mass matrix, which is pretty straightforward. But just that here the problem is so big that you have to cut that down into smaller parts and you have to run it separately. So now because you're trying to cut the problem into smaller parts, because the acceleration keeps changing everywhere, because you cannot assume the acceleration at a particular time interval, that's why your time step becomes very small when you are in explicit. Whereas in implicit, because you are on pure force or dynamic movements, that means dynamic vibrations, your time step can be larger. This time step, which we are trying to make it large in implicit, eventually you cannot make it so large that your accuracy will be damaged. So, of course, accuracy is going to cut down your time step to certain limit, and you're trying to decide between how accurate you want to be versus how fast you want to be in implicit analysis. Whereas in explicit analysis, your time step has to be small. If you try to go bigger, your simulation will not even run, because the accelerations are changing so rapidly and the deformations are happening so rapidly that if you don't capture them with smaller time steps, you'll simply skip the elements. You will see a lot of energy has not even been accounted for. And that's why you need stability to be considered when you're trying to decide the time step. So you'll see in this radius course, in future when you're running the simulations, unless you're setting the time step to a certain level, your simulation is just not going to run. Of course, because your time steps are small in explicit, your cost per time step is small, whereas in implicit, because you're trying to do a lot of things over one time step, which is supposed to be large anyway, your cost per time step is huge. Now, like I said, matrix inversion is the biggest worry for implicit, whereas so many elements being in the system is the biggest worry for explicit. So if you just double the mesh density, that means your matrix inversion is going to be even more complicated. So if I had 100 elements in the solution when I'm doing implicit versus if I had 200 elements for the implicit, my solution time will increase by 128 times. That's the meaning of it, or that's the cost for it. Whereas in explicit, it will multiply by 16 times for doubling the mesh density. So you have to be very careful when you're trying to go for higher mesh density. It always feels nice to cover the geometry nicely, but sometimes it's not worth it, because that component doesn't even get involved in the force path or in the load path. So that's more of a descriptive answer of implicit versus explicit. That question was asked a couple of times, so I thought of going very detailed on that. All right, then little picture on error rectification before solving. So it has to be very specific. It's hard to say what all errors you are going to face and how to rectify them without actually looking at an error. But the overall good practices while solving a problem in simulation is running the model checker. In Hypercrash, you had a model checker which was pretty good. You had to take the errors very seriously when model checker is trying to hint you something. Because with errors, your simulation is just not going to start. Now, those errors are going to most of the times going to tell you a nice hint what's wrong. So sometimes it will try to say that your contact type 7 and your rigid body are defining the same thing, so it's not making sense. Or sometimes you'll see that you have called something as a part of rigid wall, let's say a slave of a rigid wall, but you are also saying that it's a part of a different rigid body. So you have conflicting conditions or boundary conditions on some particular node or element. So conflicting boundary conditions, then contact interface having a very minimal gap, which is not hygienic for a solution or a simulation. Such will be the common errors or warnings. So definitely try to run the model checker, which will give you most of the hints. One more reason for many errors can be the spot welds or all the welds that you create. So in some of our simulations, we have gone by simply creating rigids because we did not see a value in modeling the spot welds. But you are always free to even convert them into spot welds if you wish. Now, the thing about spot welds is it has so many parameters inside it, which every parameter has a different meaning to it. So you have to be very careful on what you're selecting. So in some of our simulations or lectures, I have gone through some best practices. If you're following those, you'll mostly land up in a stable simulation. If you're trying to change the type of simulation, then those are the times when you try to change those parameters as well. But until then, you don't have to really explore that area that deep, as long as you're following the right numbers there, you will do well. Yeah, that's pretty much what we can say. So that's more about error rectification. It has to be very specific error before we can jump onto it. Now, questions from next person. A brief description on contact energy or hourglass energy. So hourglass energy, like I mentioned earlier, it's the energy represented by the elements that are representing non-physical modes of deformation. So what that means is your element has deformed so much that it's not absorbing any more energy. It's not also showing that it has absorbed or taken any stress, but it just shows that it has deformed. So zero strain, no stress, but it is still deformed, right? That is something non-realistic. Something is going to deform anywhere, it absorbs the energy or it reflects that energy, but you'll see strain getting formed at least, if nothing else. Now, strain being the reason and stress being the result, if you don't have strain, there is not going to be any stress. So that's the reason. Strain also gives you the formulation for energy. Because the strain is zero, there is no energy absorbed, but you still see that the element is deformed. So that's an error on the simulation side, and that happens if your element is not properly integrated. That means if you don't have those integration points properly located in your system or in your element. If there is single integration point, it's very easy to skip it when your forces are concentrated or they are rapid. Those are the times when hourglass modes are going to happen, and the energy represented by these deformation modes, which has been missed because your strain was zero and stress was zero, that is called the hourglass energy. That means somehow this deformation has happened, but it is never accounted, or it is nowhere accounted in your simulation. So that is the energy missed, or that is the opportunity missed, and that is your hourglass energy. Of course, because it's the missed opportunity to absorb the energy, you have to keep your hourglass energy under control, perhaps some less than 1% sometimes. Contact energy is represented by the energy spent in removing your penetrations that exist initially in your simulation, or the energy represented by the friction. Now, it's very hard to calculate how to get to these two separately, like what part of contact energy is represented by penetration and what part is represented by the friction. So there is an easy trick. What you could do to get a proper explanation of these, what you can do is set your friction parameters or the friction coefficients everywhere in every contact to zero. If you set that to zero, what your contact energy you will still get in the end is your contact energy coming from removal of penetration forces. Whereas once you add your friction factor, let's say 0.2 or 0.3 depending on your contacting surfaces, then you will see the energy getting more accounted for contacts, which is because of the frictions. So basically the normal force that represents the penetration and tangential force, which represented by the friction, both are getting accounted for when we are talking about contact energy.
Sir, this with that method, it will take more time because initially, if we run the model for 200 milliseconds, okay, for any simulation we run for 200 milliseconds, it will take a huge amount of time, more than 4 hours, like that. If we try to do
By
separately
which
for
method?
no, now we are telling now for identify the contact energy. First, we can set the coefficient of friction zero and find out the result that the energy is coming is due to the penetration and vice versa. So if we run model twice, it will take a twice a time.
Correct.
So is it a good practice?
Well, this is an experiment. Experiment is always, in a way, unless you learn the point of it, it's going to take time. So the point of saying that if you're trying to understand the forces represented by the penetration, that is the time when you need to run the simulation with friction equal to 0. That means you're turning one of the components off completely, just to understand how much of that quantity of the contact energy is coming from just the penetration forces. If you're not trying to understand that force, you don't have to run this. It's only for those who are trying to learn if there is any quantity that is coming only from penetrations. So yeah, it's not necessary to run the simulation twice if you're not looking for that answer. And it's completely fine to not look for that answer if you're not worried about that. Now, self-contact. Well, so self-contact in radios, we model it by using our usual common contact types, type 7, type 11, or type 19, which are all for shell elements, and then type 24, which is represented by solid elements. Now, type 7 and type 11, they have their own particular characteristics, which is basically all represented in type 19 as well. So that's a contact thing. But self-contact, why self-contact at all? So it's but natural for any link to get crushed. If you're looking at the rail of a car, you want the rail of the car to be crushed. That means it's getting crushed or it's getting deformed in a way that you'll see layers of it forming over top of each other. It's just like if you take your can of a Coca-Cola or Pepsi, the tin cans that you get, and if you try to crush them from both sides, you'll see eventually how they're getting crushed. Of course, when you're crushing them, the resistance that you're getting is valid because you're trying to crush against the length of that particular system. But after you crush it, they are getting the support from the inner layer that has been crushed. So there is, of course, this is the concept of self-contact. If you are hitting yourself, if you're touching your palms against your shoulder, this is again a sort of self-contact, isn't it? You're trying to say that a component is getting deformed in a way that it is touching itself. That's the case of can, or that's the case of your arms. So that is the practical meaning of self-contact. Now in simulation, because in type 7 or type 11, commonly what we do is we always choose a master and slave. So you say that components on this side of the contact are all masters, components on this side of the contact are all slaves. If I'm hitting a table with a hammer, my hammer is the master, my table is the slave. Straightforward. But now because we have the same component getting crushed and getting supported by the same component, we have the master and slave to be the same. And that's where you try to define the self-contact. That self-contact, the peculiar thing is your master and slave are the same straight away. So that means your calculations that are happening for contact, for every node, the contact algorithm not only looking for the element that is getting in that vicinity of gap from other components, it is also looking for the same component. If something is coming into that gap region, if it comes into the gap region, it will start following that contact algorithm by creating that 1D spring and then pushing that other element outwards. That way these self-contacts work. So self-contact is just a concept where master and slave is trying to be same because the components are getting self-crushed. Whereas self-contact is not always required. As I said, if you try to do both the calculations, whether someone is coming into contact with me or whether I'm going to come into contact with something else, if both the calculations start happening on the same node or same element, you can imagine how complicated the simulation can get. So not the entire system really needs the self-contact. If you're talking about a barrier, your barrier outer surface to your bumper does not really need a self-contact. You can clearly say which is a master, which is a slave. Whereas if you're looking at the inner components of a car, for example, your dashboard or your occupant as a system or your frontal structure of the car, these are the places where the things are going to get crushed. And that's where you need the self-contact. If I'm looking at the rear end of the car, let's say rear bumper, rear tailgate, or everything that exists in the rear side, let's say the trunks, the fuel tanks, and things like those. Again, these are the components which are not going to crush mainly if you're talking about a frontal crash. And those are the cases where you don't need self contact. So you have to be very specific here where you want to use the self contact. By looking at one simulation, you can clearly define or clearly see that, hey, I mean, this component is getting crushed, but it's not getting that physical mode or the physical way of deformation because, its elements are going through each other. It's not realistic. So that's when you are going to put the self contact in place. Significance of time step. We were talking about this when we spoke about implicit explicit as well. So time step in your simulation for crash simulations being explicit mainly. So what you're trying to do here is time step is trying to help you cut down your problem into smaller parts. Now, because your acceleration and velocity is changing rapidly from 1 second to its next millisecond and to its very next millisecond, because your acceleration value is changing, it's very hard to say that over the time 0 to 2 seconds, I can assume an acceleration of 2 millimeter per second. It's not as simple as that, right? Because it's changing rapidly. It's not like it's going from 0 to 4 within that time. It might be going from 0 to 4 and coming back to 3 over that time. And all this detail is a very important detail. That's why you're trying to even cut down this problem into smaller parts. This is where we are talk about time step. So by using time step, we are cutting down our problem into smaller parts. And during this smaller part, we are now trying to imagine our stress wave or shock wave, where the shock wave starts from one particular element, goes through that element, and as long as it can pass that entire element, that is the time we need as a minimum for the time step. So when the shock wave is going from one end of an element to another end of an element, the speed of the shock wave will depend on the material, and the time it takes for that shock wave to pass the complete element will also depend on the length of the element. So usually that's why we say that if your minimum length of an element is pretty small, your time step is also going to be affected. And that's why I was hinting that it's not a good idea to mesh with the smallest size because it's going to affect your time steps. So the smallest size of element with easiest materials decide the time step usually. And that's the significance of time step. It's really, it can take your simulation to great accuracy, but it can also harm your simulation with inaccuracy if the time step is not set correctly. Well, then there was a question from Shiva Guru about implicit and explicit, which we answered properly earlier. What are the main results required for crash and how to improve that? Very generic question. Let's try. So the main results you look for crash, first of all, after getting the simulation, this is all explained very well in the courses or the lectures in the course. You'll try to look at your energy balance. So energy itself is one of the results you would look for. And once that is done, if you are doing an occupant simulation where you're trying to unfold an airbag and hit the occupant on that, well, sure. In that case, you will also try to see the volume of the air that is getting trapped in the airbag, whether it is looking correct or not. Those are some airbag related things. For structural analysis, you'll try to see, first of all, how the deformations are happening on the rail. So just by looking at the animation, many times you will see that you have enough details there. So animation itself is a very good result, first of all. After that, you'll try to plot strain or stresses at various locations just to understand whether the deletion or the element deletion is happening at right places or not, if you had designed it for that. And then eventually you'll come down to one point where on the dashboard you're trying to measure all the deformations or all the intrusions. Now intrusion is basically when you are looking at a car, when you are sitting at the driver's seat, you have dashboard away from you by some distance, let's say 2 feet or 3 feet. Intrusion means that during the crash, the distance between you and this intrusion surface, that means dashboard, is going to decrease by a lot. And now dashboard being 3 feet away, that's still good, but your legs are so closely located with your brake pedals and the firewall beneath the brake pedals or behind the brake pedals. If those things start moving by 20 centimeter, your legs are going to be gone. So those are the points where you'll try to measure how much intrusion has happened. So to measure that, you'll measure it with respect to some standard point within your car. For example, you could be measuring it with respect to your seat base, where the seat base keeps moving along with the car. So it's a moving system. And with respect to that system, you'll try to measure how far your dashboard has come inside, or how far your brake pedal has come into the occupants or into the driver. So that's the way to measure the deformation. All of this has been discussed in the lectures going forward. Now the difference between skew and frame, asked by, actually it's not a good idea to read people name by looking at the email ID. Most of the times they are shorted, so that's fine.